investment cost versus payback, air sealing is the best one. Like, it doesn't cost that much money. You have to conceptualize it. You have to have the right materials. You have to connect it well and execute it properly, but it doesn't cost much. And that's like, if you're gonna do one thing well, do the air sealing well.
Number of different places that you can have air leaks in the building assembly. A lot of times you have air leakage coming in the basement, in the crawl space, through the windows, the rim and band joist where the house is sitting on the foundation. Air leakage coming in around windows and doors. A lot of times there's air leakage in the attic, all the tops of the interior walls, the tops of the exterior walls, top plates. There's usually a little bit of air leakage that goes through all of those spaces, and it may be just a 1/16 of an inch gap, but if you add up the area of all of the top plates for interior and exterior walls, it's a lot of air leakage. Chases for chimneys, for wire plumbing penetrations. You know when the electrician drills a hole into the top plate for a wire, they're gonna drill like a 1-inch hole and put a tiny little wire through and just leave it, and they don't typically air seal it. It's all of the little detailing work. Air sealing is very meticulous work. It takes time to go through and seal everything.
Generally, the standard house is sucking air in through the basement and sending it up through the roof. It is temperature difference that causes the exchange of air. The colder it is out, the more you don't want to lose your conditioned air. If you just let the building leak, it's going to accelerate it when it's the worst for you. The reason why mechanical ventilation just works so much better, because it says this is how much air exchange we need, and it just takes control over it rather than letting it be pressure differences that happen irregularly. Whether it's windy, whether it's cold.
I don't recommend putting your air barrier on the inside face of your assembly. You got to get into this sort of thing. You really have to pay attention with every little puncture, and then durability wise, somebody is going to be putting nails through that sheetrock to hang things. It's going to destroy your air barrier. So I like to put it in a place where you can't screw it up, like the exterior sheathing, and then you have continuous insulation on the outside of that. So you really have to work at it to cut through that air barrier.
The more that you insulate the building, the more important it becomes that you make it airtight, because the two work together. If you have leaks in high performance homes, the concentration of likelihood of rot and mold in those spots where it leaks becomes amplified, because basically all of the humidity and the heat is pressurizing through those one spot. So airtightness becomes extremely important, and that's why as the code goes up and they tell you the R value goes up, they also increase the airtightness. This is really making it airtight super easy for you. Just think about it ahead of time. Take a section of the building, think about where your primary air barrier is, whether that's a vapor barrier as well. There are plenty of times when the air barriers, even towards the outside of the wall, and you tell the electrician that you've got an airtight building, so they air seal around the electrical box. The electrical box isn't in the air barrier, so it looks like it got really well air sealed, except for the air's sneaking through someplace else and finding its way to another hole. It all needs to be in a two-dimensional plane. We have to think about the transitions, and that's making details of how those connections are made. And we are doing that by using a lot of membranes and tapes, plywood, high quality caulk. We've got all sorts of fun gaskets, and we're still using spray foam some. We have a difference between an air barrier and a vapor barrier, although they can be the same. Below grade, you want a vapor barrier. Above grade, you want a vapor retarder. So below grade, you're not going to get it to dry out the ground. The moisture's mostly being driven in from the ground. So we put a vapor barrier between the building and grade. Above the building, we have both a heating and a cooling time of year, so we're considering where the primary vapor retarder is. And that's usually the air barrier, because the air is what's going to carry most of the moisture. If you have a hole, a 1-inch hole in your air barrier that 30 quarts of water can pass through being carried on the water, whereas if you were having vapor trying to transmit through a fairly vapor open product, this is gypsum plywood. You know, it's a third of a quart of water, so that illustrates a major reason why we're doing all this air barrier stuff. Is the same thing is true with heat. Air carries all this stuff very quickly, so we want to stop the air movement. You don't want to end up making a vapor sandwich where you trap the vapor in between two products that are fairly resistant to vapor transmission. So you kind of want to decide where in the wall you want the most amount of vapor to be stopped, and consider where the dew point is. So you want that to be, ideally that's in the center third of the wall, so that the surface that it's being stopped at isn't cold enough to be the dew point. The really key point is don't let that dew point happen to the structure itself, because you don't want rot happening to what's holding your building up. We have the 4 different layers in the wall to consider. So you've got the rain barrier, basically just keeping bulk water out of the building and keeping wind from blowing through your insulation, because that can kill the R value. Then the air, the thermal barrier, and vapor was the one I was missing. This is showing how the very low perm rating, under the ground you want a vapor barrier. You don't want any moisture coming through from the ground. Also helps with radon. And then as you go up higher, you want more vapor permeance, because you just want, wherever it ends up in the wall, you want it to be able to dry in the heating or the cooling system to be able to dry out. It is worth spending the money on these high performance tapes that are designed to last 100 years. They really work well. There's tapes for around windows, the inside of the window, the outside of the window, corners. So this is showing a vapor open interior membrane. Because it was an existing building, this was the easiest way they found to making a continuous air barrier, was to wrap the inside of the space. They did their red line test and they figured out that they're going to run their air barrier on the inside of the building. So they put that up before they put the framing of the floor up. Consider how they would have made that air sealed if they had tried to come in after that floor structure was there. How would they have air sealed that? That they'd have to run around with caulk or something. If you think of your wall construction, you've decided that your primary air barrier, primary vapor barrier is going to be your sheathing. So this plywood, that's no problem to tape the seams. You can envision that that's a pretty easy way to come up with an air barrier. It's when you get to those transitions, what's happening at the bottom of the floor, how do you connect to concrete? Where in the wall is your window set, and how do you make sure that the window's taped or sealed so that it becomes continuous with your air barrier? And especially at the corners, that becomes very, like, where the 2 corners of the windows becomes 3-dimensional, and getting that intersection not to leak is a super common spot that can be problematic to people. The walls to the roof, and then there's chasing all the penetrations. And when we were discussing when to have the blower door test done, if you do that before all the mechanical systems are put in, you've got a lot less holes in your envelopes. Heat pump installer and your electrician come and show up and they blow all sorts of holes through the whole building. You got to go back and make sure and give them the gaskets and make sure that they're air sealing to the right plane in that construction, so that that doesn't end up being leaks. Here's an example of worrying about the air sealing at the foundation levels. The vapor barrier is probably coming up the outside of the foundation and the sill, and the air barrier may transition to a different plane in the wall. So they've laid a vapor barrier over the top of the concrete before they put the sill plates down, and it's flappy so that they can then flip it up when the next layer comes up and make that connection really nicely. And they sealed around all of the anchors, so they took consideration of all of that. This is an example where they are expecting the sheathing to be the air barrier and it comes up the wall, but then they were using roof trusses with a flat ceiling. They're then going to have the air barrier running across the bottom of the flat ceiling, the bottom of the trusses. So their air barrier is on the outside of the wall, and then they need it to transition to the inside. They thought ahead. They laid a piece of membrane over the top of the truss, and that's left kind of floppy so that once they get everything set, you can tape or adhere the membrane to the building sheathing, and then also to the inside air barrier that they're going to run across the interior of the bottom of the trusses. Consider how difficult that would be if you didn't think ahead. Most people aren't doing this. They're not thinking ahead, so they've got a building, and at the connection of each truss, they've got air leakage. It's really easy to do if you plan ahead. It's very difficult to do if you try to do it in hindsight. This is a scenario where the air barrier is the sheathing on both the wall and the roof, and they run the membrane that they're using on the wall up the roof so that they get a really good solid connection. That is super clean and easy. I mean, how much do you think that's going to leak? This is just showing that they found it a lot easier on the ground, make a pattern of what all the rafters are going to be, cut the membrane on the ground, and here's the tape job. So they cut that membrane to the shape of the rafter down on the ground, set it up, and then taped around. You can see the tape that runs around that rafter coming out and how much more difficult that is compared to doing it that way. Penetrations, these companies that make these membranes offer these lovely gaskets to make your life very easy. The next layer is to put a rain screen before you put your siding on. And that is not only just to let the backside of your siding dry, but it also lets vapor move out of the wall. This is like a passive house thing because we've insulated more and more and more. That outside layer is colder and colder and colder, and ending up with condensation becomes more and more of a risk. So we want to make sure, take all measures to make sure no vapor develops turning into condensation in the wall. Don't forget that you need critter blocking, and this is showing core vent, which will keep the insects out. You also need to put metal mesh. Mice will eat right through that core vent. Why do we bother? A lot of it's the health and longevity of our buildings. We are worrying about where the moisture and the rot can develop and making sure that we're managing the water. You're investing this money into these buildings, you want them to last as long as possible and not make people sick. We might have been doing it initially out of energy savings, but certainly there are many other drivers of health and comfort of eliminating drafts. Want to be thinking about spaces either in the envelope or out of the envelope. And there's a ton in the world of this, like, well, I don't heat my basement directly, but like all of my mechanical equipment's now, or like putting the mechanical equipment up in the attic. Is it outside of the heated envelope? And if it's inside the heated envelope, then you're heating it and you're putting heat into it. So when you do those energy models, it includes all space that's inside of the envelope. My point is to make it a black and white issue and not to have muddy spaces like, well, we've got a mechanical room down in the basement. We don't really need to insulate it all that well because, that's not really where we are. So, who cares? Well, it's losing heat. It is in or out. That's it. And you can not be so concerned about what the temperature is. What's the priorities is spend the money on the windows, spend time on air tightness, and devote proper planning. The red line test is just such an easy thing. You all just walk away with that. Like when you go to build something, you're gonna red line test so that you've thought ahead of time. And then when Collin shows up to do the blower door test, you're gonna pass that without any issues at all, just because you thought about where your air barrier is ahead of time.